Greetings to you all. Star e-learning platform presents to you a chemistry lesson. This chemistry lesson is going to be handling the senior 3 and the senior 4 students. It is intended to provide the necessary content that is needed by the senior 4 and senior 3 students in doing their chemistry practical, but we are even including the theory to equip them with a lot of techniques that will help them to answer the practical exam. Star e-learning platform is found on these media platforms like YouTube, Facebook, WhatsApp, Telegram. If you want to join with those to join to those platforms, you can use this number. It is connected to all those platforms, so connect using that number. One thing I want to request from you, please try to subscribe to our YouTube channel before you view or after viewing your video or your presentation. Please increase our capacity by subscribing. Press that subscription button and subscribe to our YouTube channel. This is Teacher Kadude Gracious. You may contact us through this number. You may give us a call for any inquiries or questions about our services. Give us a call. We shall be readily available to provide you our services. This is my second lesson on energy changes. Previously, a few days back, I introduced a new topic on energy changes, and energy changes, as I said, is part of the numbers that are set on in a chemistry practical. So I started off with the theory, and as I said, I shall conclude my lessons with a practical. We are still looking at energy changes. Under this, we are going to look at the types of energy changes. We are going to look at illustrations of energy changes. We are going to look at comparison of energy changes. We are going to look at examples of exothermic and endothermic reaction. We shall look at energy diagrams. We shall look at the differences between exothermic and endothermic reactions. We shall look at the standard enthalpy changes. Then finally, we shall look at the equations illustrating enthalpy changes. Let us start straight away by looking at the types of energy changes. In my previous lesson, I introduced to you an expression for energy changes, which is the H. And we said the H is given by H products minus H reactants. I remember when I was introducing my lesson, in my previous lesson, I remember telling you that before a reaction takes place, there must be an energy change. So if there is no energy change, a reaction cannot take place. It only takes place if there is an energy change. That is, if the heat in the products is not the same as the heat in the reactants. Now, if after a reaction, the enthalpy products may be more or it may be less, because what we need here is an enthalpy change, an energy change, if a reaction is to take place. So after the reaction, we expect the energy in the products to be different from that of the reactants. So therefore, the H products or heat of products may be more or less than the enthalpy of reactants or H reactants. Okay, let us look at these two incidences. We are having H products when it is less than that of the reactants. Now, if H heat of products is less than the heat of reactants, the reaction is said to be exothermic. The word exothermic simply means external. Exo means external. The word exo. So exothermic is just two words. There is exo and thermic. So exo means external, thermic means heat. So this is external heat. So in exothermic reaction, the heat of products is less than the heat of reactants. and therefore the heat change, the H, is negative. Now, if the heat of products is more than the heat of reactants, the reaction is said to be endothermic. It is said to be endothermic, and therefore the enthalpy change, the H, is positive. Okay, let us try to illustrate that more. We want to illustrate energy changes. Consider the H, or heat change. The enthalpy change, the H, is equal to the heat of products minus the heat of reactants. And if we try to summarize, the H is standing for enthalpy change. H products is standing for heat of products, and the H reactants is standing for heat of reactants. Now, assume we started our reaction when the reactants were having 40 joules. A reaction took place, and at the end of the reaction, products were having 20 joules. Now, if we try to subtract, we are going to get a negative 20 joules. Now, which means the H is negative in this case. A reaction started when reactants were having more energy. Reactants were having 40 joules. But at the end of the reaction, the products were having only 20 joules. Where has the 20 gone? Where has the 20 gone? Where has the 20 joules gone? Now that one means that there was some excess energy, which excess energy was given off to the surroundings. That's why the products are having less energy than the reactants. So the 20 joules here, they are representing the heat energy that is released to the surrounding, and it is negative. So in such a situation where the H is negative, we call such a reaction which occurs by that mechanism an exothermic reaction. So in such a situation, this DH, or the heat change, is going to be exothermic. Okay, let's look at another incidence. Okay, now consider now, if you have reactants at the start of the reaction, you had 20 joules at the start of the reaction. The reactants had 20 joules. Then at the end of the reaction, products were having 40 joules. If you try to subtract, we are going to come up with 20 joules, this time positive. Therefore, our DH is going to be positive 20. It is going to be positive 20. We started when reactants were having only 20 joules. The reactants were having only 20 joules. But at the end of the reaction, the products that we have formed after the reaction, they are having an excess. They are having 40 joules. In other words, they are having an excess of 20 joules. So that excess of 20 joules in the products is that amount of energy which is being absorbed in the due course of the reaction. As the reaction is taking place, bonds are being formed, but those bonds have an excess energy which is different from the ones of the reactants. So that's why we are having a positive 20 joules. In such a reaction where there is absorption of heat energy from the surrounding and heat of products is more than the heat of reactants, in such a situation, in such a reaction, we call that reaction an endothermic reaction. So where the H is positive, such a reaction is called an endothermic reaction. Hope you get me. Let's proceed. We proceed. Now, let us look at a comparison between energy changes of exothermic and endothermic. We have already said that in an exothermic reaction, heat energy is released to the surrounding. Heat energy is released to the surrounding. saw a negative 20, which represented the heat energy that is released to the surrounding. So as you may see those arrows, heat energy is being released to the surrounding. So therefore heat is moving from the reacting system to the outside. Okay, you get that. So in an exothermic reaction, there's release of energy from the system, and that energy is in form of heat. That energy is in form of heat. Okay, now let us look at endothermic reaction. In endothermic reaction, heat energy is absorbed. It is absorbed into the reacting system. That energy is absorbed into the reacting system. Okay, it is absorbed into the reacting system. So when heat energy is absorbed into the reacting system, of course, temperature of the surrounding is going to reduce, as we are going to see in our later discussion. So in an endothermic reaction, the system absorbs energy from its surrounding, and that energy is in the form of heat. So therefore, heat energy here is absorbed from the surrounding, as you may see here. Let's continue. Let us try to compare temperature changes with energy changes. If we look at endothermic reactions, heat energy is absorbed from the surrounding, as we have already said. So the temperature of the surrounding is expected to drop. Why does the temperature of the surrounding drop? The temperature of the surrounding only drops simply because temperature is a measure of heat. So if heat energy is withdrawn from the surrounding, is removed from the surrounding, or absorbed from the surrounding, we expect the surrounding to be reducing in its temperature. So in this case, where there is an endothermic reaction, the surrounding is going to lose heat, and in so doing, the temperature of the surrounding will also drop, or it will reduce. Okay, let's look at exothermic reactions. In exothermic reaction, heat energy is released to the surrounding. And when heat energy is released to the surrounding, we expect the temperature of the surrounding to increase. As I've already said, temperature is a measure of heat. The heat content is measured by temperature. So if we are adding heat to the surrounding, we expect the surrounding to increase in temperature. If you try to consider this diagram here, we have already said that in an exothermic reaction, heat energy is released to the surrounding. It is released to the surrounding. And the temperature of the surrounding is going to increase. Reason being, there is an addition of heat energy. So the temperature is going to increase. And therefore, the H, temperature change, is going to be positive. So therefore, in this case, we are having, if we began, say, at 10 degrees Celsius, and the temperature has risen to 20 degrees Celsius, of course, we have final temperature and initial temperature. So if we are to get the difference, we shall have to subtract the initial temperature from the final temperature. That is 20 minus 10. And we end up getting 10 degrees Celsius, which is positive. So temperature change here in exothermic reaction is positive. So therefore, the chemicals in an exothermic reaction lose energy. And when they lose energy, the H, or enthalpy change, is negative. Okay, now let us look at endothermic reaction. For endothermic reaction, as we have already said, heat energy is absorbed from the surrounding into the reacting system. So heat energy enters the reacting system. So here, the surrounding is going to reduce in temperature, and therefore the temperature of the surrounding is going to drop. Assuming we have started with a temperature of, say, 20 degrees Celsius. 20 degrees Celsius, and now we end with 10 degrees Celsius. 10. Of course, we know that initial temperature, this is our initial temperature, and this is our final temperature. Of course, if you want to get the temperature difference, we shall have to subtract the initial temperature from the final temperature. Our final temperature is 10. So if we get 10 minus 20, we are going to get negative 10. So temperature change, the H, is going to be negative. Okay, let's continue. Let us look at examples of exothermic reactions. Exothermic reactions, examples, we have acid-base reactions, or let me call them neutralization reactions. When an acid reacts with a base, there is an increase in temperature, so which means heat energy is released to the surrounding. So in a neutralization reaction where an acid is reacting with a base, such a reaction is exothermic. Another example is combustion. Combustion, example, combustion of fuels. If you try to burn fuels, heat energy is going to be released to the surrounding. Imagine lighting a candle. You use little energy of a matchstick. You light a candle, but it continues heating and burns the whole candle until it is complete. So where does that energy come from? That energy is released to the surrounding, and it causes the combustion, or the reaction between oxygen and the candle burns until there's nothing to burn. So in such a reaction where there is a combustion, it is an exothermic reaction because there is a lot of heat energy that is being released to the surrounding. Another example is reaction of water with very reactive metals. The reactive metals we are talking about here are sodium and potassium. When you try to drop sodium in water, it will produce a lot of heat, and that heat will melt the sodium. You see the sodium moving around the water. If you have dropped it in water, it will move around after melting and after producing a lot of heat. If you try to drop potassium in water, there will be a lot of heat produced. That heat produced will melt the metal, potassium, and eventually the metal will catch fire and burn. So in such a situation, that reaction is exothermic because it releases a lot of energy. In fact, they tell us to be very careful with these metals simply because these metals are very reactive. Any contact of water with them, the reaction is going to be very violent. There are other exothermic processes, not necessarily reactions, but processes. For example, dissolving sodium hydroxide in water. When you dissolve sodium hydroxide in water, the reaction is exothermic. There is heat energy evolved, especially when you're dissolving a lot of sodium hydroxide in little water. Heat energy is going to be produced. Another example is dissolving acids in water. Such a reaction is also exothermic. An example is sulfuric acid. In fact, they tell us with sulfuric acid, we don't dissolve it, we don't add water to the sulfuric acid. Reason being, the reaction is so violent, and the water will boil. If you add water in the acid, the water will boil and form steam, which steam can spill over your face, and the acid burns you. So the reaction is very violent and very exothermic. So those are some of the examples of exothermic reactions. Let's continue. Let's look at the examples of endothermic reactions. There are few endothermic reactions, but here we are going to look at majorly at the endothermic processes. For example, dissolving salts in water. If you dissolve a salt in water, for example, these salts, ammonium nitrate, ammonium chloride, and sodium thiosulfate. If you dissolve those salts in water, the reaction is endothermic. In fact, the reaction takes place by absorbing heat energy from the surrounding. If you happen, for example, to dissolve sodium thiosulfate in water, this one, if you dissolve it in water. You are going to see that this sodium thiosulfate is going to absorb all the heat energy in the water. All the heat content in the water is going to be absorbed. And in the end, the solution mixture is going to change to ice. It will change to ice. At 0 degrees Celsius, if you try to put a thermometer there, it will read 0 degrees Celsius because this salt, sodium thiosulfate, dissolves by absorbing heat energy from the surrounding. Other endothermic processes include melting of ice. If you try to melt ice, I think your teachers must have taught you about they must have taught you about the latent heat of fusion. Latent heat of fusion simply means here you are supplying heat, but the thermometer is not showing that heat. So such an incidence occurs when you're melting ice to water. You supply heat to break the ice into water, liquid water, but the thermometer will not show you any temperature change. So where does the heat you are supplying go? The heat you are supplying is just absorbed into the ice particles and breaking them apart. So in such a situation, that process is an endothermic process. Another process here is evaporation of liquid water. When you try to boil water, water boils at 100 degrees Celsius. But if you try to put a thermometer there, when water is boiling, the thermometer will not show any change in temperature, yet you are supplying a lot of heat and boiling the water. So the thermometer will show you 100 degrees Celsius. So where is the heat you're supplying going? The heat you're supplying is just absorbed to break the water particles into gaseous molecules, the gaseous water molecules. The same way when carbon dioxide is subliming. So sublimation of solid carbon dioxide is also an endothermic process. And lastly, baking of bread is also an endothermic process. All those processes take place by absorbing heat energy from the surrounding. Let us look at endothermic energy diagrams. Let us start with the exothermic reaction. Of course, this energy diagram is having an axis for potential energy and an axis for time. As time goes by, you have to supply some starting energy we call activation energy. In my previous lesson, I explained what activation energy is. I said this is the energy you supply to break the bonds apart so that a reaction can take place. And when the bonds are broken apart, these particles can collide with each other and a reaction proceeds. So here, if you are supplying heat energy to the reactants, they are going to take in energy and increase up to a maximum. The broken particles are going to be now reacting together and we form products, but products will have now, in this case, products are going to have more energy than the reactants. If you try to look at a value which would be a value of potential energy at this point, it is more than a value of reactants at this point. So potential energy at this point is less than the potential energy at this point here. Here in this case, heat energy is absorbed from the surrounding. In other words, products here are having more energy than the reactants. If you try to express in our expression, if you try to insert in our expression we have looked at here, if products are more than reactants, we shall get a positive value. And if it is a positive value, of course, a positive value is greater than 0. So that's why here the H is greater than 0. The H here is greater than 0. Hope you see it here. Let's continue. Now let us look at another application where we are having exothermic energy diagram for an exothermic reaction. Still here we shall supply activation energy, which activation energy is going to is going to break the particles, the reacting particles apart. When they are broken, a reaction takes place. Products, of course, they take in energy up to a maximum. And after taking in energy up to a maximum, products are going to form, but the products are going to have less energy than the reactants. Therefore, the excess energy is released to the surrounding. So if products have less energy here than the reactants, if you try to express or to insert in our expression we have looked at, you'll see that we are going to have the H greater than less than 0. The H, or enthalpy change or energy change, is going to be less than 0. In other words, it is going to be in negatives because it is less than 0. Let's continue. Let's look at the differences between exothermic and endothermic reactions. If we consider activation energy for exothermic reactions, in exothermic reactions, the activation energy is less than that of the one which is in the endothermic reaction. So here we have less activation energy than the activation energy in the endothermic reaction. In an exothermic reaction, we have to supply little energy. Reason being, a reaction proceeds by releasing heat energy to the system, and that energy released can support the reacting molecules to combine together and increase their kinetic energy and collision, and therefore causing a reaction to take place. So there's no need of supplying too much energy. We supply just little energy to start off the reaction. Like for example, when you're lighting a candle, you use less energy. A candle burns and produces a lot of heat energy, which can support the reaction until when the candle is complete. But when you look at endothermic reaction, you have to supply a lot of energy. So activation energy in endothermic reactions is more than that of the exothermic reaction. Let us look at the products and the reactants. Here, the energy in the reactants in exothermic reaction is more than the energy in the products. If you try to consider the potential energy here, it's not the same as the one which is here. This one is more than the one which is here for the products. So for exothermic reactions, energy in the products is less than the energy in the reactants, while for endothermic reactions, the energy in the products is more than the energy in the reactants. Another difference here, heat energy is released, while here heat energy is absorbed. Maybe another on which these diagrams are silent about is temperature. Here in a exothermic reaction, there is increase in temperature, while here there is drop in temperature. The H here is negative, while the H here is positive. Hope you get me. Let's continue. Now let us look at standard enthalpy change. What is standard enthalpy change? Standard enthalpy change here simply means the enthalpy change that occurs at standard conditions. And the standard conditions we are talking about here, they are conditions of temperature and pressure. We all carry out experiments in rooms, laboratory rooms, but the temperature in that room is considered to be standard. In most cases, that temperature is 25 degrees Celsius. If we convert it to Kelvin, it is 298 Kelvin. Still in that room, it is always 1 atmosphere. So any enthalpy change that occurs at a standard or in its standard conditions of temperature and pressure, we call it the standard enthalpy change. It is standard because it is occurring at standard conditions of temperature and pressure. Now standard enthalpy is denoted by the H theta or the H naught. Standard enthalpy is always written at the end of the reaction with either a negative sign or a positive sign. I think we have already looked at this, and we said if the enthalpy change is negative, such a reaction is exothermic. We have looked at this. If the enthalpy change is positive, then such a reaction is endothermic. We have looked at that. Now let us try to illustrate using equations. Let us try to illustrate that point with equations. Assuming we are having reacting particles A and B. We are having 1 mole of A reacting with 2 moles of B, forming 1 mole of C. And the H, which is here, which is always written on the right hand side of the reaction, it is given as the H equals negative 200 kilojoules. You are seeing it is negative. So if it is negative, it means the reaction is exothermic and the enthalpy change is negative. So what does it mean if you try to explain this reaction? What does it mean? It means that we have 1 mole of A reacting with 2 moles of B, forming 1 mole of C, and releasing 200 joules of heat. Reason being, this reaction is exothermic. So it occurs by releasing heat energy to the surrounding. So that's why it is negative. Let's look at equation 2. Equation 2 has reactants M and reactants J. Now, we have 2 moles of M reacting with 1 mole of J, forming 1 mole of H and 1 mole of T. And the H here is positive 300 kilojoules. The reaction here is exothermic and the enthalpy change is positive. So this means that 2 moles of M react with 1 mole of J to form 1 mole of H and 1 mole of T, and absorbing 300 kilojoules of heat, and absorbing 300 kilojoules of heat. Why are we saying absorbing? It's because the enthalpy change is given a positive sign. So there is absorption of heat energy, which means here the products H and T contain more energy than the reactants J and M. While here the product C contain less energy than the reactants B and A. So that's why we have those differences with either negative or positive. So the positive or negative comes as a result of either energy is released or absorbed. When energy is released, then we should have a negative sign. Reason being, products are going to have less energy because the excess of the energy is released. So the H is going to be negative, while here the H is positive. I've already explained that. So in our next lesson, we are going to look at many more explanations. I just thank you for listening to me, and I would request you one thing to do for me. Please subscribe to our YouTube channel. Whenever you reach there, place that button of subscription. Subscribe, increase the capacity of the channel. Support us. I need more support, but the simple support I would ask from you is to subscribe. Please try to subscribe to our channel. Support this channel to grow. Allow it to increase its capacity so that we post even more important information than even this one. Our YouTube channel name is Star e-learning platform e-class. So when you reach there, please view our presentations and our videos. After, you can subscribe and like our videos. Thank you so much for listening to me. May the Lord bless you